Can everyone see the slides?
Yeah.
All right, very good. Well, welcome everyone to the first meetup of 2019. Excited to get this going. I'll walk through our usual agenda. We will, these opening remarks will take a few minutes, and then we'll kind of dive into community discussion. And then I will pass the baton over to Ganesh.
There's a webinar on tonight that I want to see. Can you see the person?
Nope. Someone needs to be muted. Who will be presenting on who will be presenting on contextual bandits? All right, Zoom window, where'd you go? There we go. Okay. In terms of upcoming meetups, we've got two meetups now. There's the EMEA meetup, which is held evenings in Europe time, and the February meetup will be on the 5th, and that'll be Krishna Gade, who will be presenting on why is my classifier discriminatory. And then the February Americas meetup will be in the middle of February, evenings North America time, and that will be on active learning and crowdsourcing for machine translation. Of course, we recently sent out an email about the call for papers. We're always looking for presenters. There are lots of options in terms of available months, as well as 2 meetup time slots per month. So by all means, go hit that CFP and fill out fill out the form. You don't have to be an expert in the paper, just be interested in learning it and teaching it. So we have arrived at our community discussion. This is the kind of open mic segment of the meetup where we talk about questions and comments. Well, all of these topics that are shown here are fair game, as are other relevant topics. But here are some starters, questions and comments on recent shows, topics or guests that you'd like to hear about or hear from, thoughts on what you're working on or what's caught your interest, new papers or projects that you've seen or are working on, news items that you've seen or are working on, or just general things that you have questions about that you'd like to pose to the group. All right, so the open mic is open. This is your time. Who wants to get us going? Any takers? What do folks have machine learning and AI New Year's resolutions?
The thing that, well, I mean, I guess kind of start it off. I think what I'm very focused on these days is more of like the causal side of machine learning. I mean, it's great that we've made a lot of progress in like finding signal and predicting things. At the end of the day, we really care about, hey, if I do X, what happens? And so things and techniques related to that are something that's very interesting to me. So I've basically been spending a lot of time on those kinds of topics.
And how are you approaching that? Does that relate back to the, it sounds a little bit different, but related to the whole kind of call for rigor in machine learning?
Yeah, I mean, it's somewhat, especially with like the black box neural. I think one way to think about it, if you have a linear model or something simple, you can reason about it. You can say, if I change the input, what's going to happen to the output? With a neural network or something that's can fit a crazy functional form, that you somewhat lose the ability. So that a lot of people are working on that. But even apart from that, there's a lot of correlations that are present in data, and we all know correlations, not causation. So how can we be more rigorous about like finding things is something, you know, there's a lot of methods from other fields, allied fields, and of course the gold standard of experimentations are always there. By the way, I just noticed Adith's there, so just wanted to give him a call out. Hey Adith, glad to have you.
Hello, hello. Glad to be here.
Hi Adith.
Can you guys hear me?
Yeah.
Okay.
Awesome. Great to have you here. Great to have you on.
I was going to say, if people haven't yet caught it, in mid-March, there's going to be the, what was it called? The Science of Deep Learning, hosted at the National Academy of Sciences in Washington, D.C. It's the first time I'm seeing, it's organized by David Donahoe, Ali Rahimi, Ben Recht, Maitra, and Matan. Ali and Ben, you'll know from the Call for Rigor Test of Time Award talk at NIPS last year. It's a fantastic lineup of speakers, and registration right now seems to be open but quite expensive. So, if just go online and search for either like the Science of Deep Learning, National Academy of Sciences. It seems to be happening mid-March. I just learned about it today while I was traveling, actually.
Yeah, it sounds really interesting. Going back to your comments about causality, are there particular resources or papers that you've been finding interesting or relying on to kind of push you further into that?
Yeah, so I think a lot of the work, I mean, some of the work that I'm going to be talking about today is actually very causal in some sense, right? It's basically trying to get at, hey, if I take this action, is it going to be the best thing I can do in this situation? But a lot of the literature in causal inference, and it's changing, machine learning is coming in there, but comes from more traditional fields, econometrics, statistics, where they really, it's oftentimes a better post problem. They don't have like thousands of predictors necessarily, and then they're not trying to tease apart these causal relations. So a lot of the stuff that I've been looking at has basically literature from that side. And in fact, that's how I got into this aspect also, is because I've been trying to develop more expertise over the last couple of years in causal inference. So then, but when it comes to real world problems, observational data, it's a limitation. Like in an industry setting, I can't just go ahead and do crazy experiments. So I still have to kind of depend on, I have some control, but I don't have like control to do whatever I want. So then how do you kind of explore in the vicinity of what's possible and kind of go from there?
Interesting. You also mentioned explainability. I had a really interesting interview yesterday. I'm not sure when it'll be published, but it was with Raif Ghani, who's a professor at the University of Chicago, who's working on kind of AI for social good and AI as applied to policy types of problems. But we had this really interesting conversation about how kind of all the things that or many of the techniques that we're kind of exploring for explainability, LIME being the example that we spent the most time discussing, it's all great until you really try to put it into practice and use that explanation to explain it to a person. Relying on features of your input data doesn't necessarily provide the level of intuition that a person needs to actually come to trust the model, which made me think, kind of rethink and think, think differently about the whole space of explainability. There's just still so much work that needs to be done there. Any other thoughts, comments? We've got a couple more minutes before I hand the baton over to Ganesh.
I can mention one that's got me flabbergasted. So I lost a bet that I had with some other researchers internally in the reinforcement learning group here. We were trying to do autonomous greenhouses. There was a challenge by Tencent and a university in the Netherlands where groups across the world got to control a greenhouse in the Netherlands, trying to grow cucumbers profitably and sustainably. I had a bet that said all these machine learning methods will do much worse than human growers, and we don't have any methods that can safely and reliably take over a real world system like that without causing havoc. Turns out I was very wrong. A method based on Bayesian bandit optimization, not full-blown RL, but basically a machine learned model plus some expert guided heuristics, ended up outgrowing Dutch farmers and using much less water and fertilizer and carbon dioxide, pretty much every input than what humans use. And I'm actually kind of shocked, and I'm now trying to see, well, how can we get model-based RL to work in such settings? It seems to be a really good challenge problem to push for.
The problem reminds me a little bit of the kind of the HVAC optimization problem that Google's done in its data centers with RL. Was there something about the greenhouse problem in terms of the complexity or the number of controls that's kind of made that kind of approach wouldn't work?
When we looked much closer at the Google result, it did not use full-blown RL. It used supervised learning to build a good simulator for what the energy usage would be like under perturbations around the existing policy. Over here, I think the core of it is the growing season is about 6 weeks long or so. So every iteration of an experiment, if you're thinking about an RL trial or something like that, is just way slower. So we are not talking about energy usage on the order of 15 minutes. We are talking about like a full crop that takes many weeks to grow. But to be very fair, there isn't like a full-blown end-to-end RL system that won. I think the folks who tried to do the RL system ended up not doing all that well. It was, again, the solution looked a lot like the Google data center solution, as in supervised learning with some quantification of uncertainty.
Okay. Interesting.
What crop were you growing, if you don't mind me asking?
Sorry, what?
What crop were you growing?
Oh, cucumbers.
Cucumbers?
Yep.
Oh, cool. By the way, for more interpretability information, I found a wonderful company in San Fran called H2O. And on their GitHub, it's literally a gold mine of information. When I was going through a boot camp over the summer, they were literally my primary resource. I just put a link to what they have in the main Zoom group chat. But there's one guy there called Patrick something, but he literally helped write the paper for XGBoost. So they're like up there in terms of like awesomeness for our field.
Okay, awesome. All right, it's just after a quarter after, so I'm going to hand the baton over to Ganesh. Let me stop the share here and go ahead and take over.
Okay, let's do this. All right, are you guys able to see the slides?
Yes.
Awesome. All right, so I know Sam said contextual bandits, and that's somewhat accurate. It's not fully accurate. These topics are allied, but they're not exactly the same thing. But there is a lot of overlap between fields like causal inference, bandits, domain adaptation, and things of that nature. So I'm going to get into it, and I think as usual, we can just discuss as and when things come up. And of course, Adith's there, so he should be able to correct me if I say something completely nonsensical. Okay, so here's how the presentation structured. So first we'll start off with an introduction. Then we'll get into the meat of the presentation, which will be about the paper. But there'll be a lot of build up to it, and I'm hoping to leave everyone with at least some takeaways that they can use right away. Then we'll talk about the contributions of the paper, and I'll summarize the takeaways, and we can have more discussion at the end. Okay, so let's get started. So let's think about let's set up kind of the motivation or the framing for this problem, right? So let's say you're Google and you want to basically pick the best search result given a query and other information. Example, someone searches supervised learning. You have maybe hundreds and thousands, in fact, I'm sure millions of pages even that you can pick from. So what is the best search result is one way of framing or looking at this problem. In a similar vein, let's say it's Airbnb and you search for homes in Sausalito. And if you guys have gone through some of this stuff, Airbnb actually has a pricing algorithm. So in that case, then their question becomes, what's the best price that, and I've kind of put best in quotes here because we'll define it a bit more rigorously. But for now, let's just say there's some notion of best. And so what's the best price given a user and other information, right? A slightly different example would be, let's say it's a hospital, and this is actually one of the classic examples given, which is what's the best treatment for a patient given some patient characteristics and test information. So as you can see, all of these problems have a common thread, which is what is the best action that I can take given some contextual information. So let's kind of take this search engine scenario and kind of deep dive into it a little bit. Let's just assume we have a few users. I have 6 here, and we have some user score. So in this case, our contextual information is the user score, and maybe the user score can be low or high. And this is just trying to keep things very, very simple. And for each of these, we could either show page A or page B. So we do that and we get a result. Either we get a click or a not click, which is 1 or 0. So given this kind of data set, now the question becomes, can we pick out the best page for each user score? And the best page in this case is the action, and the user score is the context. And if you stare at this for a little bit, you'll see actually that it's not possible to really say much here, because page A always appears when the user score is low, and page B always appears when the user score is high. And so in effect, you have no exploration. When the user score is low, you've never shown page B. And when the user score is high, you've never shown page A. So without any exploration at all, it's not possible. So a simple solution would have been, let's build a classifier or supervised learning algorithm which uses the user score and action together to predict the result. And that doesn't work because we don't have sufficient exploration of the actions. And so that leads us to our takeaway number 1. We need exploration to learn good actions. And what that means is the probability of taking any action of interest given a context, which is all the contextual information, should be non-zero. So that's takeaway number 1. Now let's say we go ahead and actually do that. We go ahead and for simplicity, let's just assume there's only one context, so the user score is just high. If you remember in the previous example, even when the user score was high, there was no page B ever. So in this case, let's say we have 100 users and the user score is high for all of them. And we decide to do some exploration. Sorry, I heard someone. Okay, maybe just background noise. So let's say page A came up 99 times and page B once. So we've done some exploration here and the results were always 1. So we can kind of summarize this in a stratified way, right? So we can say for page A, when we took action A, the average result was 1, basically 99 ones divided by 99, and that becomes your average result. And for page B, you can say the stratified result, sample size of 1, and the average result is 1. So what this means is for any policy now, let's say one policy would be, I always want to show page A or always want to show page B, I can calculate what the value of this policy is. But this quickly runs into problems when the context action space blows up. So if you have just one user score and a couple of actions, okay, you can stratify. But as the number of features, imagine you have tens of hundreds of features. Now, if you start to stratify on everything, that becomes very difficult. Plus, if you have continuous variables, that also poses additional challenges. So stratification becomes cumbersome. So we need some other trick. So how about we view it this way? We take the same data set that we saw in the previous page, and we kind of, instead of having the action and the result in separate columns, we say, hey, what happened when we took when we showed page A, and what happened when we showed page B. For every user, we only showed one, either page A or page B, and the result, if we show when we showed page A was 1, and when we showed page B, we don't know what happened for user 1. And we can go down the line, and that will be the case for all the users up to user 99. For user 99, we showed them page B, and we know that they clicked, but we don't know what happened for page A. So that's kind of our scenario. So we start from there. And this is called partial information feedback, which is basically the fact that we don't know what would have happened for the counterfactual actions or the actions that were not taken. So then what we can do is we can construct a new reward. And this new reward is just the original reward divided by the probability of action given the context. We only have one context here, so it kind of simplifies. And so the probability of taking action A is 99 divided by 100, so that's 0.99. And the probability of taking action B is 1 divided by 100. And so we can construct a reward for both page A and page B based on that. So what we can do is, if we actually took the action, we take that reward that we actually saw and divide it by the probability of taking that action. And if we didn't see, we just say it's a 0 and divide it by that. And you can basically prove to yourself, it's pretty easy to see that this will also give you an unbiased estimate of any policy. So let's take a quick example. Let's say you always you always show page A. And so that just becomes 99 times you have page A times 1 divided by 0.99, that gives you a 100. So if you showed page A to 100 people, that's what you would get, and that makes sense. So this kind of technique is called the inverse probability weighting technique and allows value calculation for any policy. So that's our takeaway number 2. So calculation of arbitrary policy values is possible with inverse probability weighting. But then, and you guys might have already
describe, like in the previous slide, there was a leap that happened. I don't know if people appreciated the leap, and then why it's partial information. So if you look at the table on the left, it's useful to contrast this with supervised learning. If I didn't have all these various question marks in here, and if I instead had some numbers in there, you would notice that that is basically supervised learning. Like when you're able to have your neural network generate whatever predictions it wants, and you're able to compute a loss for every possible prediction the neural network could have made. You're able to compute a loss and backpropagate it. That's like saying that for every possible action you could take, so whether it's page A or page B, for every possible input, you get to know what the loss or the reward is, such that you can backpropagate it. So if you have a matrix of this form and there were no question marks, that would be full information, and we would be in supervised learning land. That's why supervised learning is called full information. And that's why now that we have a situation where there are a whole bunch of these question marks, the name of the game became, can we come up with ways to put in numbers in each of these boxes such that they are an unbiased estimate of what the supervised learning matrix would have looked like. And that's what sort of motivates this leap going from the left side with all those question marks to the right side, where you notice that we now have a number in every possible box.
Yeah, that's great. Thanks, Adith. So, and we also,
before we proceed, are there any questions at this time? Okay, go ahead.
Cool. So, and this might have, some of you might have already thought about this, right? We had a sample size of 1 for that action B in the previous slide. Now let's kind of make that a bit more extreme. So let's say we had action A or page A shown 999,999 times. So basically almost all the time. And once we show action B. Now you can still go ahead and the math all goes through. You can still calculate your propensity, but it's just a high variance estimator because you are generalizing based off of this one sample that you have, that action B is going to give you a reward of 1. And that's a dangerous situation to have. And so that leads to a high variance estimator. So what can we do about that? And one of the techniques that's often used in practice is called clipping. And clipping basically says it's a way of trading off bias and variance, and you'll see why in a second. But what we'll do is we take the original propensity and clip it. We say, hey, if the value is of the probability of taking an action is below a certain amount, let me just make that a small constant. And so this clearly is now not an unbiased estimate, but what you lose in terms of bias, you gain in terms of like reduced variance. So clipping kind of gives you that. So that becomes our takeaway number 3, which is clip propensities to prevent this unbounded variance. And it's unbounded because it can be arbitrarily small. If you only took the action once out of like 10 million times or a billion times, it can be very, very small. And so the variance can basically shoot up. So let's go and kind of summarize all the terminology. So I've been using a bunch of terminology. Let's kind of make that a bit concrete. So context, which is and also I have the symbols that are used in the paper, so which is going to help us set up for the next few slides. Context, which is in the paper referenced by X, an example of that is like the patient test results or the search query or whatever, what have you, right? And the action is say a stand or like page A or page B, or any of those. And the loss, an alternate way of thinking about that is the reward. Loss is the negative of the reward. And that's what the result was. So that basically what's happening in the system is you have your context and action, and they together give rise to some loss or reward, and that's your feedback. And a hypothesis, H, which is also called policy in the literature, is a mapping between a context and an action. So given a certain user comes in, or given a patient has certain test results, what should I do? And so that's kind of what a hypothesis is. Propensity, and we looked at this kind of briefly in the previous slide when we were clipping the propensities, right? Is the probability of taking an action given a certain context. And the log data that we are trying to learn from, which is basically, and we'll see this in the next slide, that's kind of the big picture is we want to learn from this log data of the past. We don't want to do an actual A/B test. We want to do something offline and learn something that'll do better than what we have. So a log data is we have context, action, propensity, and loss tuples, and we have maybe we have like how many ever, millions of them or whatever we have, and that becomes our log data. And the risk of any hypothesis is the average loss of that hypothesis. So I know that's a lot of terminology, so let me just briefly pause here in case people have any questions, or and we can kind of take it from there. Okay, let's go for it. So the big picture, we can kind of frame it this way now, right? We have the interaction logs of some existing system, 8.0, and we saw that was under partial feedback. And we kind of did inverse propensity weighting to simulate full feedback. So like Adith said, actually, it's kind of misleading to say it's true full feedback. It's like fake full feedback. And then we want to perform some supervised learning to get a new policy H, which hopefully is better than our existing policy H naught, which, and we want to pick the best action for each situation. So that's how we can kind of frame the problem that we have in terms of the terminology that we just looked at. Okay, so where are we right now? We already kind of looked at the inverse propensity weighting piece, and we're kind of here with the logs with fake full feedback. Now, let's talk about how do we perform supervised learning using this fake full feedback.
Oh, Ganesh, could I just back up a little bit and ask you to talk a little bit about the H0 of y given x? I'm not quite clear on what that means.
Yeah, okay, good question. So let's back up a little bit to this slide, right? So maybe we take a look at this slide. So H0 of y given x is basically what you would call the propensity. So in this case, we only have one context. So it's actually, x is the context, right? So the probability of taking action A in this case is 99, or actually 999,999 divided by 1 million. What I have, the inverse of this. And the probability of taking action B, which is H0 of action B given high context, is 1 divided by 1 million, right? That kind of becomes, and I see an error here, so pardon me for that. But so that's kind of the propensity, which is H0 y given x. H0 y given x just says, what is the probability of taking a given action under a certain context with our logging policy, which is what was used to capture this data. Does that kind of make it a bit clearer?
Is that the inverse probability that you're talking about, that H0 as, of y given x, is that 1 over the probability?
No, H0 is actually just the probability. It's not the one. It's not 1 over the probability. H0 is just the probability.
Okay.
Cool. Okay.
I had a question about the loss. You said the loss is the average risk. We're averaging over what? The context or the actions, or?
I think that it's a good question. The next slide will basically make that. Actually, that's exactly what the next slide is about. Okay. So we can jump ahead, and that should answer your question. So the risk, which is the average loss, is averaged over all the contexts, over all the actions that we want to take with our new policy. And that's why it says H, that's the new policy we want to learn. And that's averaged over all the contexts, over all the actions that the new policy wants to take. And this is our reward. Unfortunately, we don't have the distribution of the action. We don't have the rewards under the new policy. So we have to use the existing logged policy, H0. And we kind of looked at this a second ago, where we said, hey, if you just divide by the propensity, by the probability of taking that action, that gives you an unbiased estimator. And then you can multiply it. In the past, we assumed we're always taking any given action with a probability of 1 under the new policy, but you can make that stochastic. You can relax that assumption and say, hey, maybe 30% of the time I'll take Y1 or action 1, 20% action 2, and things like that. So it's almost the same thing, except instead of this being a 1, which means take the same action all the time with the new policy, it's a bit stochastic. You're saying, I might take some action some percentage of the time, so you're just adjusting for that. Now, clearly, this is a population level quantity, and we cannot estimate this directly, right? So we need an estimator. So what we can do to do that is we can define this inverse propensity scoring estimator. And all that does is it's summing over all the samples in our data set and taking the reward divided by P, and this quantity should be familiar to all of us by now, right? And additionally, we are just accounting for the fact that the new policy may not always take this action. It's going to take actions with like different in different proportions. It's not always deterministic. Okay, so again, let me pause there because it's kind of a dense slide, and in case people have questions. Okay, cool. Okay, so once we have this estimator, right, we can just perform empirical risk minimization, which is just a fancy way of saying, how can we reduce this risk? And since we are doing it on the empirical risk, not the actual risk, it's called empirical risk minimization. And that'll give us the optimal policy. But we still have a problem. And that problem is basically, so this table is kind of going back to our original table. We have the clipped, we have the rewards using the clipped propensity scores here. The problem basically is the fact that the evaluation of these policies is kind of chosen by them in certain sense, right? Like, let's say let's consider a policy A. And if we're always taking A, we have a policy value of 1 million, and we had an effective sample size to evaluate this policy of 999,999. But on the other hand, policy B, and we say we always took action B with this policy, the policy value is 1 million, but the number of samples for evaluation is 1. And similarly with the stochastic policy, right? So unlike in normal supervised learning, these policies are kind of picking and choosing the points that they want to be evaluated on. And we need to take that fact into account while actually optimizing for the policy. So the takeaway number 4 that I want to leave you with is account for policy variance, right? And this actually is the meat of the paper. A lot of the previous stuff has been developed, but this is the central innovation of this particular paper. So that leads us to this counterfactual risk minimization principle. So empirical risk minimization, we saw, hey, let's just find the hypothesis with the minimum expected loss, where we use the clipped propensity scores estimator, right? Now we want to do what's called counterfactual risk minimization. We want to find a hypothesis with a minimal expected loss, but we also want to account for the variance of this estimator. So this is kind of what we are trying to do. And if you went back, and I think I might actually have this in a bit more detail. So in effect, what we are trying to do is we are trying to trade off. If you compare the objective here for ERM and CRM, in CRM, we are trading off the variance with the utility of the policy, which is the value of the policy. Okay, and if you remember, this looks a lot like regularization, and that's because it is. It's variance regularization, right? Usually we might regularize on the coefficients or model complexity. In this case, we want to regularize on the variance of the policy value. Okay, so now let's kind of break down how do we include the variance in the objective, right? So this is going back to our original table. We have our, and it's a single context just to make things simple. We have our clipped propensity score based rewards that we constructed. So these UHIs kind of map to, directly map to this, right? The only addition is the fact that you also take into account what probability the new policy is going to take these actions with. And then you can kind of calculate the variance of any hypothesis using these U's. So let's say you had a policy which just takes action A, you can just calculate the empirical variance of this column. Or if it's just B, calculate the empirical variance of this column. Or if it's C, you just appropriately weight these two and take the variance. So that's kind of what's happening here. That kind of, I just wanted to put this out there to give people a flavor for what's going on behind the scenes. In reality, of course,
Ganesh, excuse me, Ganesh, I think maybe I speak only for myself, but I'm being snowed under by all the notation. I don't know what capital M is. And it's just too quick for me to be able to remember all the other pieces of notation that you've got in there. Anyway, that's just a comment.
Yeah, okay, that's a good point. I think we can slow down and take it. I think this is a good place to like kind of refresh, right? So this min of M comma H yi by xi divided by pi, that's kind of basically just saying the clipping. Remember we were performing that clipping? M is the clipping constant, basically. Does that kind of make it clear?
I have to think more about, I don't remember M being introduced, but anyway, yeah.
No, you might be right. I might not have introduced it, but I think the bottom line is it's a clipping constant, right? Yeah, I might not have put in explicitly in the presentation where M came in. So M is a clipping constant. Okay, so do other people, yeah, I think that's a good point that was brought up, which is like people might be getting lost in notation. If that's the case, speak up. I mean, it's a technical paper. I tried to make it as easy to understand as possible, but there's some limitations, obviously. So yeah, if there's any other questions, feel free to ask so that you can keep following. Okay, so assuming, and that's a big assumption that everyone's following, that then motivates this POEM algorithm. And that is basically an instantiation of the CRM principle, right? And all this is saying, and if you don't know conditional random fields, which is what POEM is based on, is just think of it as logistic regression. And that's the most straightforward way to think of it, is you're basically, for any action, you're saying what the probability is. And you can make it as simple as that. And so logistic regression has some weights, and you want to optimize those weights to give you the best policy, right? And so all we want to do is basically say, hey, what are the weights that will best optimize my objective? And you keep adjusting your weights so that your loss is minimized. So that's essentially what POEM is doing. Okay, so let me again pause there for a second before I go into experimental results, because it's kind of hard to give. It's still, I feel it might be a bit more abstract. So yeah, any questions there?
I can maybe give a statement of commentary.
Yeah, go for it.
So I think many of these are just, I would call them details. Like when you actually try to apply this to your problem, like the reason that clipping has to come in and all these things, it's really like when you actually face a problem of this form, you have a data set of this form and you better try running it, you will run into each of these issues. Like unless you do clipping, unless you do reward offsetting, unless you do variance regularization, you aren't going to get something useful when doing this sort of supervised learning on this transform data set. But I would call each of them details to get something to work. I think the bigger picture is really like understanding this distinction between what supervised learning can do, which is prediction, and what we care about, which is being able to pick an action under uncertainty. Like if you go back to that earlier matrix, you had a whole bunch of those question marks. It was partial information. We have no idea what could happen. And really the cleverness is in using this importance weighting trick to convert one of these things into the other. that like I completely agree with like the takeaways that you had, Ganesh. Like that is the big picture thing. And the other bit I'll say is in all of machine learning, I like to think of it as toolboxes. Like we have a toolbox to do classification, to do regression, to do structured learning, things like that. So I think of it as along two different dimensions. So there is, what do you do when you have a batch of data available to you and you can do whatever processing you want, versus when data is coming streaming to you in an online fashion. So the batch versus streaming, we have many algorithms for batch processing in fully informed, fully supervised situations, right? This is your favorite classification regression methods. We also have many algorithms to do streaming on streams of data when it's fully supervised. So for example, you have all this literature in online learning, mixture of experts, all those kinds of algorithms that were developed. Even when the data is coming streaming at you, but it's you don't get full information, you only know the reward for the action that you actually happen to take. We know algorithms dating back to the 1930s. This is the entire field of bandit algorithms. The thing that we found very puzzling was that there was no literature or no methods developed for batch processing of this partial information setting. So what happens if you have already collected like a few terabytes of these logs that tell you this was the action taken and this was the reward, right? There is nothing analogous to a support vector machine or a like conditional random field or a neural network or anything like a random forest. Like there's nothing of that sort if you didn't have this full information, if you didn't have like all these question marks filled in out here. So I would say like the only real detail is if you can go from this big thing to the green thing on the right, and you just try it, like all those additional details, I think are like the first thing you would try once you fill in this big matrix. So this is the conceptual leap. Everything else sort of just follows in making it work, like fixing obvious degeneracies.
Does that does that make sense to folks? Any thoughts?
I should treat silence as a no, I guess.
No, I think I completely agree, Adith. I think as I was working through this paper, that's kind of how I saw it too, which is why I have my whole thought in putting the takeaways, and I'll summarize it again in the end, is if nobody gets anything, that's still fine. As long as you carry these takeaways, you can kind of derive these principles or look them up or whatever it is that you need to do to make it work for your particular data set.
So if I can maybe try to restate just to, you know, at the highest level, the problem that we're trying to solve here to make sure that that I'm understanding and maybe it might benefit someone else. You've got this historical log of decisions that some system made, or rather actions that some system made. And I was kind of referring to that previous slide that you moved away from, or one of the slides with the matrix.
Yep, I can go.
You've got this historical log of you know, actions that a system took, and you know kind of what the user response to that action was, the score, but you can't really treat it like a label because you have no idea what the user would have done if they were shown the other action or the other option, the other page in this case. And so what this paper is basically doing is showing you a series of transformations that you can apply to your log data that will transform it into a form that you can then apply kind of known techniques to, like regression.
That's right. Yeah, basically it's a reduction problem, right? We want to reduce it to something we know how to solve.
Yeah. And the set of transformations that we're applying are essentially your 4 takeaways.
That's right. That's correct. Yeah, much more succinctly put, and I could have probably done a better job of explaining it that. Yeah.
You're doing a great job. So is there, where are we in your presentation?
We are pretty close to the end. We are basically looking at experiment setup. So I can probably go through it real quick so that we have some time left.
Okay.
People can go through the paper for more details. But just because of the fact what we are doing right now is converting a kind of a partial feedback problem into a supervised learning problem. You can do the reverse thing. You can convert a supervised learning problem into a banded feedback problem. And so that's kind of because we don't really have readily available data sets for testing bandits, unlike ImageNet or something like that for other fields. That's what this paper does, and that's what a lot of these papers do, which is take a supervised learning data set and convert that into banded feedback. And then you train kind of a logging policy using 5% of the data, and then you can train new policies from the sample feedback. So that's kind of how the experiment setup is done. And so I'm kind of just going to go through this real quick, and not people can feel free to look at the paper for more details. But the first question becomes, does variance regularization help, right? And so if you look at, and I'm actually looking at the table on the right, which says table 3. You want this loss for each, the lower the number, the better, right? And if you trained it using all the data and you had all the information, that's the skyline. And so now the question becomes, how does POEM perform against the other, like if you don't perform variance regularization? And you can see that it performs pretty well. It always has a better learned policy than what you would get from an IPS estimator. So if you didn't perform any variance regularization, you wouldn't do as well. And this was tested on 4 very different kind of data sets. And so that's pretty reassuring to see that it performs well in all of them. So then the next question is, if you keep increasing the size of your log data, does it improve? And the answer to that is also yes. And that's also reassuring because it should. Then the question becomes, what if I want the conditional random field or logistic regression returns probabilities, but we may want to have a deterministic policy. So how do you do that? You can kind of take your maximum a posteriori predictions from this logistic regression, and you can use that, and you can see that such a policy, which uses the map predictions, is still pretty good. And in fact, in a lot of cases, it should be better, ideally, because you're not doing any exploration, unlike the other one. And that is actually the case. And the fourth thing is, if you don't have enough exploration in your logging policy, what happens? Does it degrade gracefully? Does it go crazy? And it actually does degrade gracefully. So I think those are kind of like the results. And so in terms of contributions, I would say it defines the CRM principle, explicitly accounts for the variance, and then a robust implementation using CRM is POEM. And so this is mainly what I want people to take away. Like Adith said, I think the rest is details. You can get to it. But if you are trying to figure out the best action for different contexts, make sure you perform exploration and log the context action propensity and loss. And the next thing to do is perform IPS weighting, and this will correct for sampling bias. When you perform IPS weighting, you'll see that some of the propensities are pretty low. So clip the propensity weights, and that'll prevent that unbounded variance problem. And the fourth thing to do is perform variance regularization so that you take into account the fact that different policies have different variance. So that's kind of it. Yeah, so I did have some discussion topics, and folks can obviously chime in also.
I wasn't fast enough to get down the last part of the takeaways. Could you put that slide up again?
Yep, sure.
Thanks. Okay.
And Sam, is there a way that we can share? I guess I can send you the slides and you can share them so people have access to them. Yep.
We'll make sure that we put them up on the Slack along with the we'll publish the link to the video when that's up as well, when that's available.
Okay, cool, awesome.
One question I had was, is there any cause for concern that all of the experimental results were done on, not kind of organic data sets, but kind of these reverse engineered data sets?
That's an interesting question. I mean, I think Adith's probably poised better to answer, but to me, it feels like in the absence of like real world data, what are you, I mean, that's one of the best ways to perform an experiment. Having said that, I think Adith has a tutorial which shows they've also applied it to real world data sets. Adith, if you're online?
Yep. I think for the paper, we wanted to ensure it's something that's reproducible that anyone can do. So the code for all of this is available and anyone can replicate it, and also like the code for Poem and all these things. Mm-hmm. So it was very helpful to have a fully informed test set that's drawn from the same distribution as the training set. And so we can play with exactly the pattern in which those question marks show up in the training set, right? Like what is it that we don't know? But in parallel with this, we also were running this algorithm on a data set from Bloomberg. If you look at the acknowledgements in the paper, you'll notice that we acknowledge Bloomberg. We don't talk about it in the paper, but it's also been run on organic data from Criteo. And I know for a fact that at least Spotify and Netflix are also using this and have reported that, precisely this, like the variance regularization piece was super important, and without that, they were seeing degenerate results. So I think for the paper, we needed to get something that was reproducible, and anyone like we didn't want it to be like sort of a gatekeeper, right? Like only someone with an industrial system is able to even participate in this research. And in fact, following up with this paper, we sort of worked with Criteo to release a 250 gigabyte data set of organic things that allows other people to play with this and sort of validate it on a big enough validation set, even if it's not fully supervised.
Okay. Yeah, I guess the thought was more, is there something, is that the process of kind of inverting the data set introduce some kind of structure that you wouldn't find organically, but it sounds like it's working.
Well, it's a very real concern. So a very recent paper from the New York lab, I think it's, you should be able to find it on arXiv. I think it'll be called the Contextual Bandit Bake-Off. Okay. So they take, I think, 150 different data sets and run it using this sort of supervised to bandit sort of transformation. And one of the surprising findings they have is that just a greedy algorithm, don't explore, don't do any of these things, just do a greedy algorithm, seems to work pretty well, but it's happening because of a systematic bias introduced by that transformation. There is a lot of information in the features of the supervised data set that just makes the correct label sort of easy to guess. And that bandit bake-off paper is just fascinating. So you're right to be concerned about this transform not lining up with what you actually see organically in the wild.
Okay.
Could I ask some questions about some of the terminology that you've been using? I'm not familiar with conditional random field. I'm not familiar with bandit, contextual bandit. And I had another question about the role of exponential in Poem, because I didn't see anything leading up to that. and then finally, let's see, you mentioned something about importance sampling, and I know that has something to do with the plot that you made with the sharply peaked function overlaid with a less sharply peaked function, but I didn't get the role of importance sampling in this whole process.
Yeah, so importance sampling is basically the IPS weighting. So that's basically importance sampling. Regarding the exponential, so yeah, I think sharing the slides would have been easier, but here's the exponential for you in Poem. So that's your exponential function. Contextual bandits, I think that's a bigger discussion, but basically the bottom line is a bandit situation is where you don't get full feedback. And typically it's used for an online case where you're continuously able to adjust what data point you see next. Over here, we don't have that luxury. You have what data you have. So it's slightly a different scenario. And what else? I think that's probably, those were your questions, I suppose.
I guess.
Yes, thank you. And a conditional random field is the other term.
A conditional random field is basically a generalization of logistic regression, so to speak. In logistic regression, you would have like a linear feature map. You can have it as a function, and that's basically it. It's in general, you would say W times this phi, right? So that becomes a feature map. You can have any kind of feature map. So it's just a generalization of logistic regression. In fact, if you look at the code, it's actually what's being used as logistic regression.
For me, also, what it's not, I kind of get the high level process that we're applying here, but it's not very clear to me the relationship between what we're doing and bandits, contextual bandits, and in particular, the whole, one of the principles or takeaways is exploitation. And I don't really see the exploitation in the sense of the way I tend to think about bandits, like explore, exploit, and having some kind of knob that we're dialing.
Yeah, so I think the takeaway is exploration, and that basically comes from the fact that your logging policy needs to have done some exploration. If you've always given a scenario, let's take a simple scenario, right? Let's say, let's take that first thing that we saw, first slide basically. Or first couple of slides. If you're always showing the same thing to the same user, you have no way of like picking the best action. So when it's low, you're always showing page A. When it's high, it's always page B. You have no hope of picking the best action because you've never seen any other action.
I got it.
So the exploration comes from.
So exploration has to happen, and that first takeaway, exploration is like a precondition of using this. It has to be baked into your data collection process. And now that you say that, I'm remembering that from the interview that I did with Thorsten on this stuff.
Yeah, I mean, I can decouple it the following way. So the study of bandits in the streaming setting, the online learning bandits formulation, and it dates back to at least the 1930s. There's a fascinating history behind why these things are called bandits. I'd encourage anyone to look it up. But I think it's a very beautiful mathematical formalism that exposes this tension between exploration versus exploitation. Like, how do you synthesize all the information that you've got so far and do this trade-off in the best way? And there is a notion of like regret, and you want to minimize regret. That's sort of like governed all of that study. Now, in many practical applications, regret is an important and necessary thing, but it's not sufficient. Like if you already have an existing policy that's out there interacting with your users, you're just collecting data using that policy. And the question really becomes, I want a notion of progress. I want to find a new policy. I want to change from my current policy to a new one if I'm able to find something that's better than my current policy, right? And this is more a notion of progress than one of regret, right? It's like, I have an existing policy. I want to move to a new one if I'm able to find a new one that's better. And it was a bit dissatisfying that the best that we had to offer was like an A/B test, like come up with a new candidate, deploy it online on users, and maybe use bandit methodology to like do explore exploit to explore between these two policies or things like that, right? But one thing we can definitely do is like take this new policy and train it on all the data that we have already collected. So it's almost like, let's reuse the data as if it's bottled exploration. And let's settle this question of how do we best exploit, given that we already have all this exploration. Now, that's what all this paper is trying to do. But if you want to think about long-term regret, so you're not just doing this once, right? Like we had one existing system. Now we are doing this poem or whatever you want using data collected from that one system, and we are going to deploy it. If you go back and say like, actually, no, I want to ensure that there are many rounds of system iteration where we are able to do better, then you would need to take the output of something like Poem and bake in enough exploration so that you're able to do things better in the future too. So all that this paper is settling is just the question of how do you best exploit given access to good exploration. The long-term question of how do you best trade off exploration and exploitation is like not addressed at all. And like the bandit, like the online bandit terminology is like much more useful to think about that trade-off.
Okay. All right, great. I'll note for folks that want to kind of explore this more or hear kind of a slightly different take on it, I just dropped into the chat the link from the recent conversation with Thorsten Joachims. That one's titled Unbiased Learning from Biased User Feedback.
Yeah, and I can also add some resources to the, when you share this presentation, I can probably add a slide here. One of the things that I found really useful was actually Adith and Thorsten's tutorial in Sigir in 2016. I think that's basically about 2.5 to 3 hours, maybe even a bit more. And that really helped me. I must have heard it like 3 or 4 times. That made me crystallize the ideas along with reading these different papers.
Awesome. Awesome. Well, Ganesh, thank you so much for presenting. Great job.
Thank you, guys.
Yeah, thank you. This is a really stimulating paper. Now I got to go read it.
All right, great. And Adith, thank you as well for jumping in and participating. Very much appreciated.
Thanks. This was fun.
Yeah, thanks a lot, Adith, for joining. This way, people can actually hear it from the horse's mouth.
All right. Good night, everyone.
All right. See you guys.
Good night.